My dear friends. So we'll start with the second session, today's second session. So almost the SFD BMD chapter is completed. One small topic is pending. Compound beams. Compound beams means the beams joined with a pin connection. Joined with a pin or a hinge connection. So there are two times the gate questions are there. This AB the one beam, AB the one beam, BC the one beam. These both are joined by means of a pin connection. This AB the one beam, BC the one beam. These both are joined by a pin connection. The pin is driven like this now. So this pin can be seen in the top view or side view. AB is what the supported one end by a fixed support, and BC BC supported at C. AB the one beam, BC the one beam, but this AB supported one end by fixed support. BC is what now? Supported at other end by hinge support. Hinge support. This is about a hinge support. This BC joined to this support. The BC is joined to this support with the help of a pin. So this is called as, what about this black color pin now? What this black color dot is written a pin. So what the purpose of this pin now? Joining the BC to this support. This is a support and this is a beam. This beam is joined to this support with the help of a pin. So it is called about a hinge support or a pin support. But here there is no support is there. What the purpose of this pin here now? The purpose of this pin is to join this beam to this support. And what the purpose of this pin now? Join these two beams. Join the two beams. So this is called as what now? Internal hinge. Here there is no support is there. Internal or unsupported hinge. Internal or unsupported hinge. But this beam is joined to this support with the help of a pin. This is called a hinge support. What the purpose of this pin now? Join this beam to this support. So this is called a hinge support. Consider my finger as AB. My finger as AB. So this is what a one end is a fixed. This is AB. This is BC. This marker, my fingers are support. This is what a BC. This marker is a BC. It is supported by my finger. But this marker is joined to the fingers. This marker is joined to my finger with the help of a pin. A hole is going to be made, a pin is going to be driven. So what is the purpose of this pin now? The purpose of this pin is to join this marker to my fingers. My fingers are acting as a support. This marker is what now? Supported my fingers. My fingers are support. But these both are joined by means of a pin. So this is called a hinge support or a pin support. So the purpose of this pin is to join the beam to the support. It is called a hinge support or a pin support. Now this is a AB. One end is a fixed. Now these two are joined with the help of a pin. But here there is no support is provided. So the purpose of this pin is to join the both the beams. So this is called the internal or unsupported hinge, means there is no support is provided. But here there is a support is provided. Now once again what now for any beam, you want to draw the SFD, BMD, what should be the first step now? You have to find out the reactions. Total how many reactions are going to be there here now? Here 3 reactions, here 2 reactions. Fixed support 3, hinge support 2. But which reactions are 0? Horizontal reactions are 0. Number of non-zero reactions are 3. 1 vertical, 1 moment, 1 vertical reaction. Horizontal reactions are 0. Since horizontal reaction 0, you can call it as a RA. This is RA. Horizontal reaction is 0. And a moment reaction. These are the assumed directions. After calculation, if I am getting a positive, they are correct. Otherwise, direction should be changed now. Here, RCV. It is 0. So non-zero reactions are 3. Now we cannot draw the SFD, BMD. First you have to find out the reactions. So here reactions are calculated by 2 ways now. One method is here always internal hinge. This will permit the rotation. Hinge will permit the rotation. So always bendment is going to be 0. Always at internal hinge, bendment is 0. It is permitting the rotation. The permit the rotation is permitted now. Your bendment is going to be 0. So always at internal hinge, bendment is 0. Bendment is 0. Sometimes directly they are asking now. On a beam they are going to show with a dot, means there is a internal hinge. So directly what the bendment at B means 0. Bendment at B is 0. Now, first, how to find out the reaction now? One method is what now? Write down the bendment at B and equate to 0. Write down the bendment at B and equate it to 0. Bendment at B and equate it to 0. Better to consider right side or left side? No, right side. If we consider right side directly, what if bendment is what now? 10 into 1 minus 10 and RC into 5. RC into 5 positive. So RC into 5 is equal to 10 into 1. So RC will be 2. Here bendment is 0. But we cannot take the left side because there are 2 unknowns are there. But here only one unknown is there. So one method is what? Write down the bendment at B and equal to 0. Better to consider which side? Now right side. So by using this one, you can find out the RC. Once you know the RC, then RA can be calculated by using sigma V is equal to 0. So once you know, then this you can calculate by using sigma M is equal to 0. So one method is what now? First method, to determine reactions. First method to determine reactions. Write down the benefit B. If I take the right side, 10 into 1, right side clockwise negative, anti-clockwise is positive. So from this one, RC will be 2. I am getting a positive. Positive means assumed direction is correct. Once you know RC, so what the other method now? How to find out RA? So this I am getting plus 2. Means upward. Then by using sigma V is equal to 0. By using sigma V is equal to 0. Upward is positive. RA minus 10 and RC upward you are taking positive. So from this one RA will be 8. I am getting a positive. Assumed direction is correct. Then what about the moment reaction? Moment reaction can be calculated by using sigma M is equal to 0. So I take a negative. Anti-clockwise I am taking negative. And what the moment due to this now? Clockwise. Clockwise are positive. So 10 into 6. Next, RC anti-clockwise 2 into what the total distance? Now 10. So MA will be 40. I am getting a positive. Positive means assumed direction is correct. That is anti-clockwise. So once you know the reaction, you can complete the SFD BMD. So this you are getting as 8. This is 40. So directly what the benefit at A? Minus 40. In the question is asked what the benefit at A? Minus 40 hogging. So what the shear force at A? 8. What the benefit here? No, 0. Benefit is 0. So this is one method. What the other method of finding out the reaction? What the other method to find out the reaction? Remove this pin. Remove this pin. Isolate the both the beam. Separate the both the beam AB and AC. AB and BC. Remove this pin. Isolate it. Separate AB and BC. Then introduce the two dummy forces at B. Two dummy forces at B such that they are equal and opposite. Why you have to introduce it now? Because of this load, what happens now? This beam will be deflected downward. After joining, what happens? Both will act as single beam. There are two separate, but both are joined by means a pin. After joining, what both will act as a single beam. Both will act as a single beam. So due to this load, this beam is deflected downward. It will deflected downward. Then automatically this beam is also deflected downward. So here deflection will be same. Deflection is same. So what the action of this second, if I am calling this a second beam, is the first beam, where the load is applied on the second beam. So what the action of the second beam under the first beam? Downward. Then at that time the first beam will offer a reaction. Action of the second beam onto the first beam will be downward, and the reaction of the second beam onto the Reaction of the first beam onto the second beam is going to be upward. So what do you have to do it now? What the other method now? Remove the pin, isolate it, then introduce the two dummy forces such that they are equal and opposite. One will be action, one will be a reaction. Second method to determine reactions. So due to due to this load, this beam is deflected downward. So at that time, what the action of this, I'm calling the second now, the first. So what the action of the second beam and the first beam downward. After joining, both will act as single beam. Here deflection will be same. So what the compatibility equation or deflection is same. So deflection of the first beam and deflection of the second beam at B is going to be same. So when this beam is deflected downward, it is also deflected downward. So here action will be downward. So that I am calling as about RC, RB. This is about the action of the BC onto AB. Then at that time AB will offer a reaction here now. AB will offer a reaction. AB will offer a reaction. Now this looks like about now simply supported beam is a cantilever beam. Now we cannot find out the reaction. First you have to find out this RB. Now you can use your shortcut method. It looks like about now simply supported beam. This is a cantilever beam. Now to find out this RB by using the shortcut method, 10 into what the distance with the other end and what the span of 5. So 8. Then automatically this is what now you have to calculate. Sorry, this you have to calculate it now. 8. So sum of this reaction should be 10. So already when RB is 8 means RC will be 2. 10 minus RB 2. So when this is what this reaction is 8, here action is also going to be 8. Now this will become as about a cantilever beam subject to a point load. So what the reaction of the cantilever beam now? Vertical reaction equal to net vertical load 8. And moment reaction is clockwise. This is about a clockwise means moment reaction is anti-clockwise. What the moment now? 8 into 5, 40 clockwise. Therefore reaction is anti-clockwise. That's all. Either you can use that method or this method. What the advantage of this method now? No equation. There you have to use the 3 equation. But here is what now? No equation. It is just like a simply supported beam and the cantilever beam. Once you know the reaction, directly you can give it now. So once you got the reaction, mark it in the actual beam. Then you draw the SFD BMD. Now can you give the directly what without any calculation, without drawing the SFD BMD? This is the second method now. The second method. Once you got the reaction, you mark it here and draw the SFD BMD. Any beam, once the reactions are same, reactions are calculated for every beam, SFD BMD concepts are same. But without drawing the SFD BMD, can you give the without drawing the SFD BMD, can you give the shear force and bendment now? Cross section, shear force, bendment. A the extreme end. At A, what the shear force now? 8. Bendment is what now? Minus 40. Next B. A to D. There is no load. Between A and D. Between A and D, there is no vertical load. Therefore, directly shear force is going to be constant. Between two constant point load, shear force constant. Therefore, here also shear force is going to be what the same. So, what the shear force at B? 8. But what the bendment now? 0. Next at D. D the junction. There are constant point load here. 2 shear force are there. So, shear force should be calculated 2 times. Bendment should be 1 time. So what the shear force here now? First neglect it. I am taking the right side. If you neglect it, right side upward is going to be what? Otherwise, like the left side now. Neglected. What the shear force now? Plus 8. Now considered 8 minus 10 is what now? 8 minus 10 is what? Minus 2. So what the shear force at D? You have to calculate 2 times. Larger of 1 is 8. And 8 minus 10. So what the larger value now? 8. And what the bendment at D? Bendment at D, better take the right side. Anyone you can take it on the right side. What the right side bendment now? 2 into 4. 2 into 4 is what? The 8 positive. At C, what the shear force now? 2. And bendment is 0. So every time you need not draw the SFD BMD now. So what the maximum bendment now? Minus 40. Minus 40. It is a minus 2, sorry. Minus 2. So where the shear force changing sign at D? How many shear force are there at D? 2. When D belongs to left side, what the shear force? 8. When D belongs to right side, what the shear force? Now minus 2. So where the shear force changing sign at D? But maximum bendment is going to be A. Even though shear force changing sign at D, but bendment I am getting maximum at A because of what now? Couple. Whenever a couple is there, what now? Shear force bendment need not be maximum where the shear force changes sign. Shear force changing sign at D, but bendment you are getting maximum at A. So what the maximum shear force now? 8. Maximum shear force is 8. Otherwise, you can go for the SFD BMD. Every beam what? No, same. Left hand side upward is positive. Is a +8. What is the next step now? Where the next constant point to D? So A to D is a constant. Next is the downward negative. 8 minus 10. Now once again, if you have the maximum bendament, everybody is going to consider D. For shear force changing sign. But here bendament is may not be maximum because couples are there. So this is a SFD. And what about the BMD? Here bendament is 0. What the bendament at A? Left side clockwise positive, anti-clockwise negative. It is 40. And bendament at B is 0. So when shear force constant, it will vary linear. And what the bendament at D? Better take the right side. 2 into 4, 8 positive. Shear force changing what a sign at D, but bendament is maximum at A. I have already mentioned, my dear friend, this load is acting on this now. This beam is downward what now? This beam is deflected downward. So this beam is also deflected downward. So when this beam is deflected downward means what now? Action will be downward or upward now? Where the load is applied on this now? Load is applied on this beam. So both beam will be deflected downward. So this beam and this both will be deflected downward. So when this deflected downward means what now? Load will be in the downward direction or upward direction? Downward. Action downward. Reaction will be upward. If you want, you can change it also, but you will get a negative value. You will get it. You can check it now. You can take this downward, this upward. You take it now. You are going to get a negative value. You will get it now. So always remember what at internal hinge bendment is 0. at internal hinge bend moment is 0. So reactions can be calculated by two ways. One is what now? Write down the bend moment at B at internal hinge, bend moment at B, internal hinge, and equate it to 0. So you can find out one reaction, other one you can find out by using sigma V and sigma M. Otherwise, what the second method now? Split that beam into two parts by removing that hinge. Since the load is acting on the second beam BC, so its action onto the first beam AB is going to be a downward. So reaction of the first beam AB onto the second beam is going to be upward. So then you can, one will become as a cantilever, one will become as a simply supported. Now this will become as a statically, this type of questions are there in the next chapter also, deflection of the beam. You are going to start it now. Suppose here I am going to provide a one more fixed support. Some students are calling it a propped cantilever. It is not a propped cantilever beam. Probably morning somebody was asking, no, it is not a propped cantilever beam. Is it a single beam or two different beam? Is it two different beam? It is not a single beam. Suppose if I am going to remove this now, if it made as a single beam, it is a propped cantilever beam. It is not a propped cantilever beam. There are two beams are there. AB the one beam, BC the one beam. Both are joined by means of a pin. It is not a propped cantilever beam. Propped cantilever beam is single beam. But there are two separate beams are there joined with a pin connection. Either compound beams or beams joined with a internal hinge or a pin connection. Now, suppose if I am going to provide a fixed support here now, in place of the hinge support, if I am going to provide a fixed support, if it is calling a fixed beam, it is not a fixed beam. Two cantilever beams joined with a internal hinge. So I am going to provide a fixed support now. If it is going to call the fixed beam, it is not a fixed beam. Two cantilever beam joined with the help of a pin. Two cantilever beam joined with a pin connection. Now in that case what happens here, how many reactions are going to be there now? Two reactions are there, one vertical reaction, one moment reaction. Then this will comes under what? Statically indeterminate. Then we need a compatibility equation required now. In this chapter, we are giving always what? One is a fixed support, other is a simple support. One is a fixed support, other is a simple support. But if both are fixed support, these questions cannot be completed in this chapter. To complete this question, we need a deflection of the beam chapter concept is required now. If a question is like this, if it is going to call this a fixed beam, it is not a fixed beam. Two cantilever beam joined with the help of a pin connection. But it is a statically, both are statically indeterminate. In the previous case, this is a statically indeterminate. Why now? How many unknowns are in this beam now? RB unknown, RA unknown, MA unknown. Three unknowns are there. We cannot find out the reaction. But here only two reactions are there, RB and RC. So two reaction can be calculated by using sigma V and sigma M0. So since you have calculated RB, then you got this RB, then you have calculated now. But if you go for this one, what happens now? If I take the left side, how many unknowns now? RD and moment reaction. Here also about the RA and moment reaction. Here how many reactions will be there now? how many unknowns are going to be there now? 3 unknowns. Here also 3 unknowns, 3 also unknowns are going to be there now. Now if I write down the bend method B, we cannot find out RD is also unknown is there, MD is there now. So here we cannot find out the reactions. AB is also cantilever beam, BD is also cantilever beam. Both are statically indeterminate. RB, RA, MA. Here W, RB, now here this is also statically indeterminate. It is also statically indeterminate. How many equation? Only 2, sigma V and sigma M. Unknowns are 3. Here also 2 equation, unknowns are 3. Both are statically indeterminate. Then how to do this question now? Compatibility equation required. Here deflection will be same. Both are acting as single beam. So after applying the load, what happens now? Both are going to be equally deflected. Then you have to use the compatibility equation. Deflection of the first beam at B, deflection of the second beam at B should be equated now. Then we'll get the RB. This beam is deflected downward. If I'm calling this second beam, is the first beam. So here deflection is same. Then how to solve this question now? What should be the first step I have to do it now? If I'm calling this the first beam, is the second beam, deflection of the first beam at B and deflection of the second beam at B equated, then you can find out the RB. Once you know the RB, then you can find out by using sigma V is equal to 0. We can find out RD. And similarly, by using sigma M is equal to 0, we'll find out the moment reactions. Moment reaction. Same thing, you can use this equation for this beam now. So if you want to complete this question, we need a which chapter required now? Deflection of the beam chapter required. So in the end, completely SFD, BMD, what type of questions are there now? Compound beams. One end is the fixed support, other end is the hinge support. So simple support is given, hinge support is given now. In all year in the SFD, BMD chapter, the compound beam questions are going to be one end is the fixed support, other end is the simple support is going to be there. But if 2 fixed supports are there, 2 fixed supports are there, so both are statically indeterminate. So here these questions cannot be completed in the SFD BMD chapter. So these questions can be done only after knowing the deflection of the beams now. So these questions are given in the deflection of the beam chapter now. Always statically indeterminate beam. Statically indeterminate beam, the reactions are determined with the help of the compatibility equation. The compatibility equations are written in terms of the deflections now. So to find out the RB, I should know the deflection. Is one cantilever beam subject to point load at the free end. Is a cantilever beam subject to point load. One RB upward, one W downward. And most of students are calling as about the fixed beam. You have mentioned fixed beams are not in the syllabus now. It is not a fixed beam, 2 cantilever. Previous one is what? One cantilever and one simply supported joint. So 2 questions on the workbook. Similarly, how to find out RA now? By using sigma v equal to 0. MEA is going to be calculated by using sigma m equal to 0. Now read on the next chapter now. Chapter number 4, deflection of the beams. In gate paper 2 times the questions are given now. So always remember at internal hinge, bend moment is 0. Next one is what now? Deflections are equal. At internal hinge or unsupported hinge, bend moment is 0 and deflections are going to be equal. Since the deflections are equal, then you can equate the deflection of the both the beams, then you can find out the reactions. But that is compulsory when if both the beams are statically indeterminate. But whatever the question I had taken now, in this case the right side is about a simply supported beam, so directly can find out the reaction. We don't need a compatibility equation. So this compatibility equation required when both AB and BC, both the beams are statically indeterminate. That is possible when both are going to be supported both the end by fixed support. Third on the chapter number 4, deflection of beams. This chapter is with respect to rigidity criterion. This chapter is with respect to rigidity criterion. First write down the aim of this chapter now. Aim of this chapter. Aim of this chapter is to, write down the aim now. Aim of this chapter is to derive expression for maximum slope and maximum deflection. Maximum slope and maximum deflection for various beams. Under different loading conditions. For various beams under different loading conditions. Various beams under different loading conditions. Next point. The maximum slope and maximum deflection equations. The maximum slope and maximum deflection equations are used in the design of beams. Maximum slope and maximum deflection equations are used in the design of beams and design of shafts. Design of beams and design of shafts based on rigidity criterion. Design of shafts based on rigidity criterion. And in the determination of natural frequencies. In the determination of natural frequencies of the shafts. Natural frequency of shafts under transverse vibration. Natural frequency of shafts under transverse vibration. You are going to study 3 vibrations: longitudinal, transverse and torsional vibrations. Longitudinal vibrations are due to axial load. Transverse vibrations are due to transverse shear load, TSL, and torsional vibrations are due to twisting couples. Next point. Deviation of the longitudinal axis of a structural member. Deviation of the longitudinal axis of a structural member under axial compressive loads. under axial compressive loads is known as buckling. Is known as buckling. Is known as buckling. Next point. Next point. Deviation of longitudinals of a structural member. Deviation of longitudinals of a structural member under transverse shear loads. Under transverse shear loads. Under transverse shear loads is known as bending. Is known as bending. Next point. Next point. Beam undergoes two deviations while it is bending. Beam undergoes two deviations while it is bending. Beam undergoes two deviations while it is bending. That is linear and angular deviation. Linear and angular deviation. Linear and angular deviation. Next point. Linear deviation of longitudinal axis of a beam. Linear deviation of longitudinal axis of a beam is known as deflection. Is known as deflection. Linear deviation of longitudinal axis of a beam is known as deflection. Next point. Angular deviation. Angular deviation of longitudinal axis of a beam. Angular deviation of longitudinal axis of a beam angular deviation of longitudinal axis of a beam is known as slope. Is known as slope. Next point. Slope and deflection due to shear force. Slope and deflection due to shear force. Slope and deflection due to shear force are very smaller in magnitude. Are very smaller in magnitude in comparison to in comparison to slope and deflection due to bendiment. Slope and deflection due to bendiment. Hence slope and deflection due to shear force are neglected. Hence slope and deflection due to shear force are neglected. So what the aim of the chapter? Now you have to derive the equation for expression for maximum slope and maximum deflection, where they are used now in the design of the beams and design of shafts based on rigidity criterion, as well as in the calculation of natural frequencies of the shafts under transverse vibration. Next, what you are given about the bending and buckling. What the difference between bending and buckling? Deviation of the longitudinal axis of a structural member under ACL, axial compressive load, is known as a buckling, and deviation of longitudinal axis of a structural member under transverse shear load is nothing but a bending. But starting what the bending you have studied now. Bending means what you have studied now. Bending and a twisting. Rotation of a cross section about polar axis called as a twisting. Rotation of a cross section about HCA or VCA you called as a bending. Some students will ask now, sir, initially you mentioned rotation of a cross section about HCA. This is the HCA. Bending. Rotation of the cross section about VCA you called a bending. But here you are telling deviation of the longitudinal axis of a structural member under axial load is a buckling, under transverse shear load is a bending. When both are correct only. So what the meaning of bending you have to mention now? Anyone you can give it. Rotation of a cross section about HCA or VCA, or deviation of the longitudinal axis of a structural member is also known as bending. But when you have to use this rotation word now, there you have studied the difference between twisting and bending. So if you ask what the difference between twisting and bending, what now? When a cross section rotates about polar axis, twisting. Rotation of a cross section about HCA and VCA is bending. So if you ask twisting and bending, use the cross section rotation, you can use it now. But if you ask bending and buckling, in that case use the deviation of the longitudinal axis of a structural member under axial compressive load is the buckling, under transverse shear load is going to be bending. Like this now. So my two hands are the cross section. Is the longitudinal axis remain horizontal. Two cross sections are parallel. This is what a hogging or sagging now. These cross sections are rotate like this. It is a sagging. Top fibers have come nearer now. Then at that time this axis will what now? Deviate. How long the axis will remain horizontal? How long the axis will remain horizontal? When the cross sections are going to be parallel. But whenever you apply bending, in presence of bending, what happens now? This is what now? Rotation of a cross section about HCA is a bending. Which bending now? Sagging. Top fibers have come nearer, bottom fibers are going to be far away. Bottom surface length is increased, top surface length is decreased. This is called as a sagging. Then automatically axis will what now? Deviate. Axis will remain horizontal when now? When the cross sections are parallel. So whenever the cross section rotate about HCA or VCA, that is bending. Means in this case top surface gets contracted, bottom surface elongated. In that case axis also going to be deviated. So bending means what you can call it now? Rotation of a cross section about HCA or VCA. Is the rotation about which axis now? HCA. Or you can also use the deviation of the longitudinal axis. But if you ask the difference between bending and twisting, use the which definition? Rotation of a cross section about HCA, VCA is known as bending. But if you ask difference between bending and buckling, then use the word of what now? Deviation is better now. If you consider what this is a spring, is a spring, short spring. It is a tall spring. Length is what? Here length is going to be less. Length of the spring is less, diameter is more. If I push it like this, what happens now? A short spring, length is less, diameter is more. If I push it like this, only length will decrease. A tall spring, length is what now? Very large. Length is very large and diameter is very small. In this case, if I am going to push it like this, so before length reduction, what happens? The axis is going to be gets deviated. So if I push it like this now, before length reduction, what happens? The axis is going to be gets deviated. So the deviation of the longitudinal axis of a structural member under ACL, my two fingers are offering which load now? Compressive load. Compressive load. So at that time, the axis is going to be gets deviated, longitudinal axis deviated. That is called as what now? Buckling. So the longitudinal axis is going to be gets deviated. Longitudinal axis gets deviated either due to axial loads or due to bending moment. But due to axial load is called as what? A buckling. Due to transfer shear load is called as what? A bending. And whenever the axis is deviated, there are two deviations there. One is the linear, one is the angular. That linear deviation you are calling as the deflection. Angular deviation is calling as slope. Actually, the angular deviation, not the slope. Slope is about now? Tan of angular deviation. Slope means dy by dx. The dy by dx equal to tan theta. So tan of the angular deviation. Tan of the angular deviation is the slope. But for smaller angles, tan theta equal to dy by dx. For smaller angles, tan theta equal to theta. Hence, the theta is equal to dy by dx. So strictly speaking, slope is not the angular deviation. Slope means what you have to give it now? Actual one is what now? Tan of the angular deviation. Tan of the angular deviation is going to be a slope. But for smaller angular deviation, the slope, that is the tan theta means slope, that is equal to theta. For smaller angular deviation, slope and angular deviations are equal. That's why generally they are calling it the angular deviation is called as a slope. But strictly speaking, the tan of the angular deviation is going to be a slope. But in the entire chapter, what is the major assumption? Already starting your study chapter to chapter, some assumptions are there. In this entire chapter, we are neglecting the slope and deflection due to shear force. We are considering only due to bending moment. What is the reason now? Already given the reason. Slope and deflection due to shear force are very smaller in comparison to slope and deflection due to bending moment. That's why all the beams, when you have done the strain energy calculation, in all the beam in the strain energy calculation, in all the beams, strain energy calculations, we are not consider strain energy due to shear force, you are considered only bending moment. When slope and deflections are less, work done is going to be less, the strain energy is going to be less. So default always what now? Whatever the equation you are going to derive, they are all valid by considering the bending moment only. So one of the major assumptions in this chapter is the slope and deflection due to shear force are neglected because they are smaller in comparison to slope and deflection due to bending moment. There are four methods are going to be there. One is the double integration method, Macaulay's method, moment area method, Castiglione theorem, and one more is the conjugate B method. 5 methods. In all this method, what is the default assumption now? We are considering slope and deflection due to bending moment only. Slope and deflection due to shear force is neglected. But I'm covering only 3 methods: double integration method, Macaulay's method and not Macaulay's method, double integration method, moment error method. Other one is the Castigliane's theorem. I am going to consider it now. Castigliane's theorem. Based upon my class notes of deflection of the beam, you can answer only objective questions. Some of the conventional question means examination. Whatever the notes I am giving, that is not sufficient. We need some more extra information required for mains examination. But already for this objective examination itself, it will take the 10 hours or like this to complete this topic. Now, around 10 hours is required now. But if I go for conventional, it is still time taking now. So we are covering only for GATE and ESC prelims only. Remaining chapters, you can also do the conventional questions of other chapters based upon the class notes. But based upon the class notes, you can complete only objective questions can be what now? Completed. Conventional questions cannot be completed. For conventional questions, sometimes we need the Macaulay's method as well as what now? Macaulay's method is required. But civil engineering students, they are also studying the conjugate beam method. Conjugate beam method is not in the syllabus of mechanical engineers. So only apart from a class notes, you need some more information for mains examination. That is going to be Macaulay's method is required. That I am not discussing. My aim is to what? Thus my students should able to complete the all the objective questions of GATE and ESC or any examination within a less time and more accurate. That I am discussing. Some batches have discussed the Macaulay's method, but finally nobody is using that method now. Because always the student need aim is to what? Get the correct answer within a less time. So for that one, we need the double integration method, moment error method and Castigliane's theorem. Now to explain the slope and deflections, I am going to take the three cases here now. To explain the slope and deflections, I am considering one simply support beam, cantilever beam as well as simply support beam under unsymmetric loading. What is the represent of cantilever beam? What is longitude axis representing now? Initial position. How long the axis will remain horizontal when there is no load. So this is the initial position of the beam, that is when there is no load acting. Now I am taking example of the beam is subjected to constant point load at the free end. Subjected to constant point load at the free end. So because this beam is subjected to circular bending or what now? Is it subjected to pure bending or simple bending? Simple bending. Pure bending is possible when you apply bending couples at the extreme end. It is a simple bending. Shear force and bend moment both are zero. Pure bending is possible only when the bending couples are applied at the extreme end. But here shear force and bend moment both are non-zero. It is a simple bending. In this case, the beam will bend in the form of a non-circular or parabolic shape you are getting. Yesterday, how many shapes you have studied? A circular or parabola straight line. When you will get a circular, shear force 0, bend moment is going to be constant. But here shear force is non-zero. Next, shear force and bend moment both are 0, straight line. But whenever shear force is non-zero, bend moment is varies. Then in that case, you are going to get a parabola. So I am drawing the shape of this now. This is the initial position. Now this red color curve is known as what? A red color curve is known as what now? Elastic curve or maximum deviated position of the beam. This is what now? Elastic curve. This here representing by EC. EC. So this represents the maximum deviated position. And what about the black color line? Initial position. Final. Or maximum deviated position. What about this line now? Initial position is the final position. How many shapes you have studied? Now 3 shapes. Circular or parabola, straight line. But this is going to be a parabola because of what now? Shear force is non-zero. When shear force non-zero, your shear force is non-zero constant. Non-zero constant means bendment will vary linear. Then it is a parabolic shape. You are going to get it now. Now this deviation, this is called the deviation, linear deviation. This is called the deflection. In cantilever beam, always deflection maximum at the free end. In cantilever beam, always deflection maximum at the free end. So when I'm going to the free end to fixed end, what happens? Angular deviation, linear deviation, deflection will decrease. So always in cantilever beam, deflection maximum at the free end. And when I'm going to the free end to fixed end, deflection will decrease. And finally, fixed end deflection is 0. At the fixed end, deflection is 0. So this is called the linear deviation. Linear deviation. That linear deviation here calling as what? A deflection. But where now? At free end. So when I'm going to the free end to fixed end, the linear deviation decreases, that the deflection will decrease. Now how to get an angular deviation? How to get an angular deviation? Once again, what this B is representing now? What this B is representing? A cross section of the free end. And what this B1 is representing now? What this B1 representing now? Final position of the cross section at the free end. What this dot B now? This B is about now? Cross section at the free end, initial. Now what this B1 is representing now? Final position of the cross section at the free end. Final position of the cross section at the free end. Now how to get an angular deviation? To get an angular deviation at the free end, draw a tangent to the elastic curve, this elastic curve. Draw a tangent to the elastic curve to get an angular deviation. So what this tangent is representing now? What is this blue color line? Tangent for the elastic curve at the free end. This tangent, blue color line is the tangent. Tangent to the elastic curve at the free end. This is representing what? What this tangent is representing now? Final position of the cross section at the free end. And what about this line is representing the initial position of all the cross sections. This line is representing the initial position of all the cross sections. Initially all the cross sections are what? A parallel. So long it acts the horizontal. But what about the B1? B1 is representing what? A final position of the cross section at the free end. And this black color line is the initial position. Now this angle is called as what now? By how much angle is rotated by the cross section at the free end. Once again, this will be a maximum. So always in cantilever beam, slope and deflection are maximum at the free end. So actually this will be about now angular deviation. What is black color line? Initial position of the cross section at the all the cross section. But what about this tangent is representing the final position of the cross section at the free end. So this representing what? Suppose the x radian. What this x radians is representing now? By how much angle the cross section is rotated about which axis now? HCA. This will give a bending in which plane? In a vertical plane. The bending is in which plane? In a vertical plane. Vertical plane means about HCA. So what this theta is representing now? By how much angle the cross section at the free end is rotated about its HCA. Rotated about its HCA. And the tan of this theta is called as the slope now. Tan of this theta is the slope. And the tan of the theta equal to dy by dx of this now. But for smaller angle, tan theta equal to theta. So that's why what this theta you are calling as a slope. But strictly speaking, tan of this theta will be called as a slope now. Now once again, if I want to get some midpoint somewhere now, C. I taken an arbitrary cross section. C1. So this representing deflection at cross section at C. Deflection at cross section C. This YC is less than YB. YC is less than YB. YC is less than YB. And finally, what the deflection at A? Deflection at A is 0. Why the deflection 0? Because the vertical reaction, fixed support will restrict all the motion. Fixed support will restrict the axial motion. Vertical motion, rotation is restricted. So since the vertical motion restricted means vertical reaction is 0. So vertical reaction, vertical motion restricted means what? A deflection 0. But vertical reaction non-zero. What the RA value? No, W. When a reaction is going to get it now? Reaction you are going to get when? When motion is restricted. Your vertical reaction 0 or non-zero? Non-zero means vertical motion is restricted. That's why deflection 0. So always in cantilever beam. Now this YC is less than YB. So always in cantilever beam, deflection will be maximum at the free end, 0 at the fixed end. 0 at the fixed end. So when I am going to the free end to fixed end, the deflection will decrease. Similarly, how to get what now? What the angular deviation of this cross section at C? What the angular deviation of the cross section at C? So whenever you want to get an angular deviation, once again at C, draw a tangent to the curve. Now this is theta C. Now once again you can check it now. Theta C is less than theta B. Theta C is less than theta B. Means, and what about theta? Once again here no, 0. Fixed support will permit the rotation or restrict the rotation. When rotation is restricted means angular deviation is 0. So here once again angular deviation is 0. Fixed support, both slope and deflection are 0. What is the reason now? Fixed support will restrict the both vertical as well as what now? Both vertical motion restricted as well as what now? Rotation also restricted now. When the rotation restricted means what now? Slope is 0. When the vertical motion restricted means deflection 0. So always in the cantilever beam at the fixed end, both slope and deflection are 0. And both are maximum at the free end. Both are maximum at the free end. When I'm going to the free end to fixed end, both are going to be decreases. Both are decreases. And finally 0 at the fixed end. But some students will ask now, sir, you have taken theta in the clockwise direction. We are mentioning this line is the initial position, this is the final. Can I measure in the anti-clockwise direction, sir? What this theta is representing now? By how much angle the cross section at the free end is rotated. This is what now? Tangent. You are measuring like this. Some students will ask, sir, can I measure in the anti-clockwise direction? Theta should be measured always in the direction of rotation. Theta should be measured always in the direction of rotation. This beam is rotated in the clockwise, anti-clockwise. No, the beam will be rotated in the clockwise, anti-clockwise, clockwise. It will give you a bendment in clockwise direction or anti-clockwise direction. Clockwise. Since the bendment is what? A clockwise. The beam will rotate like this now. What the direction of the bendment? Clockwise. So the beam will rotate in the clockwise direction. So always theta should be measured in the direction of rotation. By chance this load is upward, this load is upward. It will give a bendment in which direction? Anti-clockwise. So beam will rotate in the anti-clockwise. Then theta should be measured in the anti-clockwise direction. So theta should be always measured in the direction of rotation. Direction of rotation decided by the direction of the bendiment. And direction of the bendiment depend upon the load acting on the beam. By chance the upward, the beam will rotate in anti-clockwise. Then you have to measure the theta in anti-clockwise direction. Theta in anti-clockwise direction. Now, what the blind way? No, without seeing the direction of rotation. Direction of rotation depend upon the direction of the bendment. Here only one load is there, and that load is what? In the clockwise direction, is giving a bendment in the clockwise direction. So without seeing the direction of rotation, that is without seeing the direction of the bendiment, how to decide directly theta direction? Actual method is what? Now you have to see the bendiment direction, and bendiment direction depend upon the load acting on the beam. If the bendiment direction is clockwise, therefore you have to measure in the clockwise direction. So without seeing the direction of rotation or direction of bendiment, in which direction I have to measure blindly now, without seeing anything? Always measure the theta in a direction such that it should be less than 90. Now this value is less than 90 or more than 90? Less than 90. And what about this value? Now more than 90. Suppose they 20 degrees. What about this now? 160. So always theta should be measured in a direction such that it should be less than 90. In which direction you are getting less than 90? Clockwise, anti-clockwise. Anti-clockwise I am getting more than 90. Clockwise direction I am getting less than 90. So those you are unable to identify direction of rotation or direction of the bendiment, blindly measure the what? A theta in a direction such that it should be less than 90. In this direction less than 90, the more than 90. In cantilever beam, at free end, both slope and deflection are 0. Sorry, maximum. Theta is maximum. Theta is maximum and deflection is maximum. At fixed end, both are going to be 0. Now we are coming to the simply supported beam. Now for the aim of this chapter, you have to derive the equation for theta max and y max. In your tabular form, those you are going to refer that deflection of this table form now. This will be how much now WL cube by 3 EI. And this will be how much now theta max is WL square by 2 EI. This will be what now? WL cube by, we are going to derive it also, 3 EI. Yesterday also when you have done a question on impact loading, you have done it now. This is a C2. Is the C2 value now. And what about this theta max now? C2. Here this you are called as a C1. They're only given in the question, tabular form is given. Probably this is the third case in the tabular form. So when a cantilever beam subjected to point load at the free end, C1 is what a 2 and C2 3. So beam to beam only C1 and C2 values are changes. Beam to beam C1 and C2 values are changes. That only given in the tabular form now. The third standard case in the tabular form is what now? Third case. C1 is a constant for maximum slope. C2 is a constant for maximum deflection. We'll derive it what now? 2 and 3. But always you have to remember this, all the standard equations. Here in this case, is what now? What is the shape of the elastic curve? In the previous case, what is the shape of the elastic curve? Parabola. Because shear force is non-zero, bend moment is varying. Shear force a constant, bend moment is what? A varying, linear. It's a parabola. What is the shape of the elastic curve? Once again a parabola. It is also simple bending. Here shear force 0 or non-zero? Shear force non-zero. Bend moment is also non-zero, bend moment is varying now. When shear force non-zero means bend moment is always what? A varies now. So it is about once again a simple bending. What is the shape of the curve now? Once again the elastic curve is going to be a parabola. Most of students they are going to draw a circular arc. Circular arc you will get it only in case of what now? Circular arc is possible only when shear force 0, bend moment is constant. But here what bend moment is not constant. Bend moment is constant only when the bending couples are applied at the extreme end. It's a simple bending. Simple bending means what you have said now, shear force non-zero. Whenever shear force is non-zero, means bend moment is going to be varies. Whenever a bend moment varies, radius of curvature varies. Then it's going to be a parabolic shape. So once again, this is about a symmetric loading or unsymmetric loading. The symmetric loading. What is the example? A simply support beam under symmetric loading. So deflection will be maximum at the mid span. Deflection maximum at the mid span. So whenever a simply support beam under symmetric loading, deflection will be maximum at mid span. Then how to get a slope now? To get a slope, what you have to do it now? Draw a tangent. Now this is a tangent. Now this tangent is parallel to axis of the beam. So here slope is 0. So what is the first conclusion now? Whenever simply support beam under symmetric loading, when simply support beam under symmetric loading, when simply supported beam is under symmetric loading, deflection will be maximum at the mid span. Slope will be 0. Slope will be 0. Now here deflection 0. Always at every support which is 0 now. Every support which is 0. How many supports you have studied now? 3. Roller, hinge, fixed support. Every support deflection is 0 because every support they are restricting the vertical motion. Every rigid support always deflection 0. Every rigid support, which reaction? Common vertical reaction. Once there is a vertical reaction means what now? It is restricting the vertical motion. Once vertical motion restricted means deflection 0. But every rigid support slope is not 0. If the slope should be 0 means what the condition? A rotation to be restricted. Which support will restrict the rotation? Fixed support. Only at the fixed support slope is 0. But simple support will permit the rotation or restrict the rotation. Simple support will permit the rotation. That's why moment reaction 0. So when they are permitting the rotation means what? Slope is non-zero. So always at the fixed support both slope and deflection are 0. At fixed support both slope and deflection are 0. But simple support, roller and hinge, only deflection 0. Slope is non-zero because of they are permitting the rotation. So here slope is non-zero. How to get the slope here now? To get a slope, draw a tangent to the elastic curve. Draw a tangent to the elastic curve. Now shall I measure the theta and what this now? Longitude axis. This tangent is the final position. Now I have to measure in the clockwise anti-clockwise direction now. In which direction I am getting theta less than 90? Theta I am getting less than 90 in anti-clockwise direction. Therefore this will be a theta. Theta. And this will be a theta max. Why should be measured in the anti-clockwise direction? Strictly speaking, a reaction upward. This reaction will give a bend moment in which direction now? Anti-clockwise. But without all this thing, how to check it now? This is what a more than 90. Clockwise I am getting more than 90. Anti-clockwise I am getting less than 90. That's why you have to measure directly in the anti-clockwise direction. Here once again, draw a tangent to the elastic curve. Here in which direction theta is less than 90? Clockwise direction less than 90. Why no? Here reaction upward. This will give a moment in which direction? Clockwise. So here theta should be measured in the clockwise. Once again, this is the maximum. So what is this figure representing now? Simply supported beam under symmetric loading. Simply supported beam under symmetric loading. For the first conclusion now, at midspan, deflection is maximum and slope is 0. At supports, slope is maximum. So in what way this differ from the cantilever beam now? In cantilever beam, both slope and deflection are maximum at the free end. Both are 0 at the fixed end. But here, slope is maximum at the supports, deflection maximum at the midspan. Slope is 0 at the midspan, deflection 0 at the supports. So here, in cantilever beam, 0 slope and 0 deflection are always at the same location, that is the fixed end. And maximum slope and maximum deflection both are at the free end. But in simply supported beam, slope will be maximum at the supports, deflection maximum at the midspan. But under which beam now? Under symmetric loading. And simply support beam, slope is 0 at the midspan, deflection 0 at the supports now. So 0 slope and 0 deflection, maximum deflection and maximum slope locations are going to be different. But there, 0 slope and 0 deflection, maximum slope and maximum deflection will occur at the same cross section. Next, what is the other now? Slope at the supports. Slope at the supports are equal unlike. One will be a clockwise, one will be anti-clockwise. Unlike means opposite direction. Here the clockwise, here anti-clockwise. And always remember now, whatever may be the condition, whether it may be a symmetric loading or unsymmetric loading, always maximum deflection will occur where slope is 0 and vice versa. In simply supported beam, whatever may be the loading, symmetric or unsymmetric, deflection will be maximum always at the cross section where slope is 0 or vice versa. Otherwise, 0 slope will occur where the deflection maximum in simply supported beam. In simply supported beam, is 0 at the cross section where deflection is maximum. And vice versa. this is for any loading. This is for any loading. Sorry, this is for only symmetric loading, and this is for any loading, means maybe symmetric or unsymmetric. Whatever I written, these are all for only for symmetric now. This condition for any loading, maybe symmetric or maybe unsymmetric. That is both symmetric and unsymmetric loading. Symmetric and unsymmetric. Unsymmetric loading conditions. Symmetric means already I studied. Symmetric means only one load or multiple load. Even multiple loads may be there now. But symmetric means, what the condition for symmetric you have studied now? Same magnitude of the load should act at the same distance and in the same direction from both the supports. Same magnitude of the load should act in the same direction and same distance from both the supports. Timing I have taken a one load. Suppose here one more load is a W by 2. Here one more load is W by 2. At the same distance, W by 2 downward, W by 2 downward. At a distance of what now? L by 4, here also L by 4. Means symmetric. Symmetric. So once again, these are all valid now. So what the difference between simple support and fixed support? Already I studied a day before yesterday now. When you have studied the supports now. At simple supports, always moment reaction 0 because they are permitting the rotation. Fixed support, moment reaction non-zero because they are restricting the rotation. Next, at simple support, slope is non-zero. But fixed support, both slope and deflection are 0. At fixed support, both slope and deflection are 0. But simple support, only deflection is 0. Slope is non-zero. At simple support, deflection is 0. Slope is non-zero. But fixed support, both slope and deflection are 0. Fixed support, both slope and deflection are 0. And for this case, what the C1 now? You can check it, maybe this is a fourth case is given now. What the C1 value now? C1 and C2. In the tabular form, fourth case now, 16 and 48. C1 is the constant for the slope, C2 the constant for deflection. So what the maximum slope now? In the previous case, what the constants now? Here what the C1 and C2 now? C1 is 2, C2 3. C1 is 2 and C2 3. But here 16 and 48. So what should I write on the maximum slope here now? WL cube by, WL square by C1 EI. What the C1 now? 16 EI. And maximum deflection WL cube upon C2 EI. What the aim of the chapter was written now? You have to derive the equation for maximum slope and maximum deflection for various beam. But for all the standard conditions, you have to remember it now. So instead of remembering the total equation, you have to remember the what now? C1 and C2. Maximum slope is WL square by 16 EI. In the previous case, WL square by 2 EI. In the previous case, maximum deflection WL cube by 3A, but here is 48. So instead of remembering the total equation, you have to remember the C1 and C2 should be remembered now. But all these equations are derived because of the bendment only. In all this derivation, what now? Slope and deflection due to bendment are considered. Slope and deflection, shear force are neglected. So these are all only due to bendment. Shear force is going to be neglected. Everybody is going to try a circular arc. It is not a circular. Circular arc is possible only when shear force is 0 and bend is a constant. That is a pure bending case. Next, I am taking the one more example. Now, what is the difference between this example and this now? It is a symmetric loading, is unsymmetric loading. Unsymmetric loading. Which reaction is more? Now, this reaction more. In the previous case, reactions are equal, same direction. Symmetric loading means what now? Both the reactions are equal and upward. Symmetric loading means reactions are always equal and they are in the same direction. Is the unsymmetric loading. So this reaction is more and this reaction less. So in this case, once again, what the shape of the curve now? Parabola only you are going to get it. But deflection, where it is maximum now? Deflection neither maximum at B nor at C. Everybody is going to tell what the previously load is acting at C. So deflection maximum at C. Now your load is acting at B. They are going to mention deflection maximum at B. It is not incorrect now. In the previous case, load is acting at the mid span and the symmetric loading. So there deflection directly maximum at the mid span under symmetric loading. But this is the unsymmetric loading. Unsymmetric loading. Unsymmetric loading. In this case, deflection neither maximum at B nor at C. That is deflection neither maximum at the point of application of load nor at the mid span. It will be between B and C. It will be B and C. So we don't know the location of the maximum deflection. It will be between B and C, but we don't know exact location. But in the previous case, deflection maximum at the mid span and slope is 0. And bendment is not maximum at the mid span. Bendment is maximum at B, you are going to get it now. Bendment is not maximum at the mid span. But here bendment is maximum at the mid span. Is what this is representing now? Simply supported beam under unsymmetric loading. Under unsymmetric loading condition. simply support beam under unsymmetric loading. In this case, already mentioned now, deflection neither maximum at B nor at C. It will be in between point of application of load and midspan, that is in this region. It is a region of Y max, but where exactly we don't know. Region of Y max, but slope is maximum at A. In the previous case, slope is maximum at both the supports. In the previous case, slope is maximum at both the supports, but here slope is maximum at a support which is nearer to the load. For this load, which support is nearer? No, A. Slope is maximum at A. So in this case, slope at the supports are unequal, unlike. But in the previous case, slope at the supports are equal and unlike. But here slope at the supports are unequal, unlike. Unequal. Here maximum, it is not maximum now. Here once again, every support which is 0, no, deflection is 0. But theta is going to be maximum here now. Is a maximum. And here at D, once again deflection is 0. But theta D is non-zero, but is not maximum now. But less than theta max. It is non-zero, but less than theta max. But how to find out the maximum deflection here now? How to find out the maximum deflection? How to find out the location of the maximum deflection? It will be between B and C. That is between what now? B and C. But where exactly we don't know. Then what you have to do now? Whenever a deflection maximum, what you have studied now? In simply support beam, slope is 0 at the cross section, where deflection maximum and vice versa. So whenever deflection maximum, slope is 0. In the last chapter, we have written the shear force and bendment equation. Now here you have tried on the slope and deflection equation. Slope and deflection equation. So to find out the maximum deflection, what I have to do it now? First, equate the slope equation to 0. Take a section between B and C. Write down the slope equation and equate to 0. Get the value of x, and that should be substituted in the deflection equation. Take a section between B and C. Then write down the slope and deflection equations and equate the slope equation to 0, because when the slope is 0, deflection maximum. So equate the slope equation to 0, get the value of x, and that should be substituted in the deflection equation. In the region between point of application of load and midspan, and slope is maximum. Maximum at a support. Which is nearer to the point of application of load. Application of load. Point of application of load. And slope at the supports. slope at the supports are unequal and unlike. Slope at the supports are equal unlike. So if you ask find out the maximum deflection, what you have to do it now? First you have to take a section between B and C. Slope equation should be equal to 0. You take a section between B and C. We don't know exactly between B and C. So equate the slope equation to, you are going to discuss next now, how to write in the slope equation, equal to 0. You'll get some x is equal to x star. X is equal to x star. That x star value lies what now? If the x is measured from the left side, x star value lies between L by 4 and L by 2. If the x is measured from left side, x star value lies between L by 4 and L by 2. Next, the same thing you have done it in the morning now. To find out a maximum bendment, what you have done it now? Equated the shear force equation to 0. Got the value of x and substituted in the bendment equation. Same thing here also what now? Equate the slope equation to 0. Get the value of x and substitute that value in the deflection equation. Then you are going to get a maximum deflection. Now this is about now 11th case, last case in the tabular form, and I called what now? This is A and this B I called it. If you can refer the tabular form, this distance I called the A and this distance is B. So here check it, theta at B. So these are the last case equations are given in the tabular form. But what the last case speciality? These are what now? Not maximum slope and maximum deflection. Slope is maximum where now? At A. Deflection maximum between B and C. Remaining all the cases, probably 11 cases are given. I not remember exactly 11 cases. Probably this is 11th case now. So remaining all the cases are given the equation for maximum slope and maximum deflection. But these are not the maximum slope and maximum deflection. Both are giving the slope and deflection at B. Both are giving the slope and deflection at the point of application of load. But till case 10, all are given what? The C1 and C2 are given. That the maximum slope and maximum deflection equation. Maximum slope and maximum deflection equations. So this case, that's why probably in the tabular form I kept as what a star. This case is not what now? Is unsymmetric loading, and whatever the equations, they will not give the maximum slope and maximum deflection. They will not give the maximum slope and maximum deflection. They will give the maximum slope and deflection at the point of application of load. But remaining 10 cases are going to give the tabular form C1 and C2. C1 and C2 are what now? they are going to give the maximum slope and maximum deflection. Here slope is maximum at A, deflection maximum between B and C, but these equations are what now? At the point of application of load. But how to cross check whether the equations are correct or incorrect now? When this case will become as this case now? When this case will become as what is this case? X is equal to A equal to B is equal to L by 2. This load is acting exactly the mid span. Load is acting exactly the mid span. Means A is equal to B is equal to L by 2. So this last case will become as this case. Now probably this is the fourth case in the tabular form. Fourth case. So the 11th case will become as the fourth case when now? When A is equal to B is equal to L by 2. Now when A is equal to B is equal to L by 2 means load is acting exactly mid span. At the mid span slope is 0. Now if I put it A is equal to B is equal to L by 2. If I put it A is equal to B is equal to L by 2, 0. And here deflection maximum, how much you got it? Now WL by 48A. So if I put the A is equal to B is equal to L by 2, this should become 0 and this should become as what now? WL by 48A. A is equal to B is equal to L by 2. L by 2 whole square, L by 2 whole square what now? L to the power of 4 upon 64. Sorry, L to the power of 4 upon 16. 16 into 3, 48. If A is equal to B is equal to L by 2, this case will become as symmetric loading. In this case, then you are going to get the theta B 0. WL by 48A. L by 2 whole square, L by 2 whole square. That is the L to the power of 4 upon 16. 16 into 3, 48. L to the power of 4 upon L cube. These equations are used in our vibrations. What the advantage of the equation now? What the advantage of the equation? We can find out the slope and deflection at the point of application of load. But generally for design you are interested in the maximum slope and maximum deflection. But sometimes these are also required now. Find out the slope and deflection at the point of application of load. This is case 11 now. I'll take the one more example. They're all important for objective examination now. Maybe this may be the fifth case is given in the tabular form now. This is asked directly in one of the exam is asked now, gate paper now. So what is the difference between this example and this example? This beam is subjected to constant point load at mid span. But in place of constant point load here, which one is acting? A concentrated moment or a bending couple. This beam is subjected to constant point load at mid span. But this is concentrated moment. So what is the difference now? Here point load is acting at the mid span, constant point load. Here concentrated moment or bending couple. So what is the difference now? First difference is either symmetric loading, either unsymmetric loading. Everybody is going to take this as symmetric loading. It is not a symmetric loading. Symmetric loading means reactions should be equal in the same direction. Here reactions are equal in the same direction. What are the reactions in this case now? W by 2. Here reactions are what now? Equal but unlike. One is the downward, one is the upward. So what is the difference now? We are making a comparison between what now? A simply support beam subjected to point load at the midspan and a concentrated moment at the midspan. First difference is what is symmetric loading is unsymmetric loading. Next, at midspan, deflection maximum, slope is 0. Here deflection maximum, slope is 0. But here slope is maximum, deflection is 0. In one paper they asked deflection here, no, directly 0. But slope is going to be maximum. When a point load is acting at the midspan, try to write down this comparison now. First difference is what now? It is a symmetric loading, is unsymmetric. We are making a comparison between simply support beam subjected to a constant point load at midspan. Left side I am taking this case now. And a constant moment at the midspan. At the right side I am taking now. So the symmetric, unsymmetric. This is symmetric and the unsymmetric. And what the next now? At midspan, deflection is maximum, slope is 0. Here slope is maximum, deflection is 0. Next. Here deflection 0 only at two locations. Deflection 0 only at two locations, A and B. But here deflection 0 at what now? A, B, C. Deflection 0 at 3 locations. But previously what now? Here only 2 locations, A and B. But here deflection 0 at the 3 locations. Next. Here slope is maximum at the supports. Here slope is maximum at the supports. But here slope is not maximum at the supports. Slope is not maximum at the supports. Slope is maximum between support and midspan. Slope is maximum, sorry. Slight correction. Slope is maximum at the supports. But here slope is maximum at the midspan. Slope is maximum at the midspan. Here at A and B is not 0 now. So not maximum now. If it is going to mention slope is maximum at the supports now. That is valid what now? In case of symmetric loading. But unsymmetric loading, slope is maximum at the midspan, not at A and B. Next, your deflection maximum at only one cross section C. But your deflection maximum at the two cross section between A and C, C and B. Between A and C and C and B. And here there is no point of counterfacture. No point of counterfacture. But here point of counterfacture will be there now. What the AC? What the bending in AC negative? What the bending in BC positive? Means AC is the hogging. CB is what now? AC is what? Hogging. BC is the sagging. This bending is what? A negative. Here positive. Therefore AC is in what now? Hogging. And BC is what now? Sagging. Means point of counterfacture will exist. But here there is no point of counterfacture. Complete BB the sagging. The concave or convex upward now, concave upwards. But here what the shape we are going to get it now is a hogging. Hogging means what? A convex upward. So what the shape of the curve here now? Convex upward. And this is sagging. The concave. You can be thorough with this word. You can understand this sub chapter thoroughly if you are thorough with the last chapter. And this is called the point of inflection. This is called the point of inflection. point of inflection. What is the point of inflection now? What is the point of counterfacture? Where the bend moment is going to be changes its sign. Bend moment is changes sign. And that can be seen in the BMD. But what the point of counterfacture? Where the shape of the elastic curve changes from convex to concave or vice versa. This changing from what now? The convex and concave or vice versa. The point of inflection can be seen in the beam. Point of inflection is the cross section. Point of inflection is the cross section where shape of the elastic curve changes from convex to concave or vice versa. Whenever a point of counterfacture, point of inflection will be there. Whenever a point of counterfacture is there, always point of inflection will exist. But point of counterfacture can be seen in the BMD. That is what now? Where bend moment is changes sign. Point of inflection can be seen in the beam. That is what now? Where shape of the elastic curve changes from concave to convex or vice versa. But in this case, no point of counterfacture, no point of inflection. No point of, completely what now? Concave. But here concave and convex. Sir, this also is unsymmetric. But unsymmetric means default you are taking as a constant point load. But this is what now? It is also unsymmetric but constant moment. So these conclusions are not valid here now. These conclusions are valid when now? Unsymmetric loading means what? Default unsymmetric loading means we are taking a concentrated loads. But this is what now? Moments now. Concentrated moment. What is the shape of the BMD? This is called the point of counterfacture. So here at C, deflection is 0. Slope is maximum. This is ml by 12 EI. So C1 is 2. Here C1 is 2. C1 is 12, sorry. Not 2, 12. But A and B deflections are 0, but slopes are half of the maximum slope. So deflection 0 at A and C. So obviously deflection maximum between A and C. Here also now. Both are different. Point of counterfacture and point of inflection are different. You can see I shown it here. Now this is the point of counterfacture. Point of counterfacture can be seen in the BMD. Point of inflection is seen in the, no. What is the point of counterfacture definition now? Point of counterfacture is the cross section where bend moment is going to be changes its sign. It can be seen in the BMD. And point of inflection is the what? A cross section where shape of the elastic curve. Whenever a point of counterfacture, always point of inflection is there now. but this can be seen in the beam now, that is the elastic curve. Point of inflection in the cross section where shape of the elastic curve changes from concave to convex or vice versa. So quickly I am going to compare it. I don't know whether you are written or not now. But the comparison now. Left side I am taking a simply supported beam subjected to point load at the constant point load at the midspan. And right side is what a simply support beam subjected to concentrated moment at the midspan. So what the first difference now? Is a symmetric loading, unsymmetric loading. Next, at the midspan deflection maximum, slope is 0. Here slope is maximum, deflection is 0. Next, here deflection 0 only at the two locations A and B. Generally deflection 0 at the supports now. But here deflection not only 0 at the supports, but also 0 at the midspan. Next, slopes are here maximum at the supports. Slopes are maximum at the support, but here slope is maximum at the midspan. And what the slope at the supports now? Half of the maximum slope, half of the maximum slope. Next, here deflection maximum at only midspan, deflection maximum only at the midspan, but here deflection maximum between A and C and C and B. Deflection maximum between A and C and C and B is the maximum deflection, maximum deflection is also maximum deflection. So maximum deflection will be at the two cross section between the support and the midspan. Next, here point of counterfacture will not exist. Point of counterfacture and point of inflection will not exist, but here point of counterfacture and point of inflection will exist. Once a point of counterfacture is there, automatically point of inflection will be there now. But point of counterfacture can be seen in the BMD. Point of inflection is what is seen in the beam now. Once point of counterfacture is what now? When the bend mode changes sign means shape of the elastic curve also changes now. But if you ask the definition, what you had mentioned now? Point of counterfacture is the cross section where bend mode is going to be changes its sign, that is sagging to hogging. That can be seen in the BMD. Point of inflection is the cross section where shape of the elastic curve changes from convex to concave or vice versa. And here reaction symmetric loading means reactions are equal and like, but here reactions are equal unlike. So this question directly asks what is the maximum slope now. What the slope is asked at C. It didn't ask all this thing. This question is given workbook probably 5th question now. What the slope at C? Slope at C. But options are given like this now. Slope at C. Some students have taken 0. Sir, symmetric loading, sir, symmetric loading, deflection maximum slope is 0. It is not a symmetric loading. Some students have taken 0. And some students who has attended my lecture, they have given the answer is A. But answer I have given in the workbook is C, I have given now. And everybody is what now? Sir, in the workbook you are given the different option. ML by 6A, but in the class note you have written ML by 12A. Both are correct. Here I have taken the span is L, but in the workbook question, gate paper is given, span is 2L is given. This L is given, this L is given. So in place of L, what should I put? No, 2L. Then answer is going to be ML by 6A. Sometime not only should remember the simply equations. Everybody what? Simply what now? This question is matches with the 5th case in the tabular form. Directly the selected option A. But I given the what option is what when the span is L. But in the question span is given what now? This is given. So what the span of the beam? No, 2L. So in this place, what I have to take? No, 2L. If I put the 2L, answer is going to be ML by 6A. Slight changes are going to be there. Slight changes are there. That's why try to go through the question thoroughly. But most of students, what now? The given question in the work exam is matches with the is given tabular form. Case number 5 or 6 now. Directly they've selected A. So please go through the question thoroughly, each and every word. All my expressions are valid when span is L. Length is L. Span and length are equal in cantilever beam. But in the question, check it now whether span is given L or 2L is given. You have to check it now. With this, now my introduction almost 1.5 hours now. So they are going to be useful sometime. 4 or 5 questions. 4 or 5 questions asked. Some several times is asked now. But these are all valid what? Sir, this is also unsymmetric. This also, but this unsymmetric means default you take a constant point load. Default unsymmetric means what now? This is that is concentrated point loads. Some students will what now? Sir, you mentioned unsymmetric loading. Deflection is maximum in the region point of application of load and midspan. Then it should be maximum here. Sir, slope is maximum at the support you have mentioned, sir. But you are mentioning the slope is what now? These are all valid what now? Assuming the concentrated point loads. But the concentrated moment. That only mention each and every conclusions are valid under a given condition. Should be careful now. How to show the slope here now? How to show the slope? How to show the slope? Now draw a tangent. So this is about the slope. What the theta you have studied now? Angle between the what a tangent as well as the longitude axis. So this is theta. Theta max. Theta max. In which direction you have to measure it? Now clockwise. In which direction? Less than 90. Less than 90 is what a clockwise. If you measure like this, more than 90. And this couple is also in which direction? Clockwise. So you have to measure the theta in the direction of the couple. Because of what now? This is going to be what now? Less than 90. This angle is more than 90. But here slope at the supports are equal and like. Now you can see now this slope now. If you draw a slope tangent here now, this is anti-clockwise direction. Here also it is anti-clockwise direction. So what the one more difference now? Generally the slope at the supports are unlike. But here slope at the supports are like. When a constant point loads are there, slope at the supports are unlike. One is the clockwise, one is the anti-clockwise. But in this case, slope at the supports are what now? Slope at the supports are, both are anti-clockwise. Both are anti-clockwise. So this is anti-clockwise. Theta A. Once again you draw a tangent. It is also anti-clockwise. So what the one more difference you can make it now? Here slope at the supports are slope at the supports are equal unlike. Slope at the supports are equal unlike. But here slope at the supports are equal and like in nature. It is also anti-clockwise. It is also anti-clockwise. So this is one more difference. Here slope at the supports are, these are all what are important because of MSQ questions are possible. A simply support beam subjected to concentrated moment at midspan. Which of the following statement are correct? At midspan, slope is 0, deflection is maximum. Deflection is 0, slope is maximum. Slope at the supports are equal and like in nature. Slope at the supports are equal and like in nature. Slope at the supports are equal unlike in nature. What the answer? No, B and C are correct. Like this, what so many questions are possible now. So MSQ, these are all important now. Some students are what now? Sir, why you need? I am not appearing for a university examination to write down the differences. You are not appearing for a mains or university, but you are appearing objective. But any of the questions are going to be possible now, especially because of MSQ. These are all important now. Most of the students, they will take the what? Slope at the supports are unlike, they will take it. That is possible in case of what now? Constant loads. But here what now? Slope at the supports are equal and like. But here equal and like. One is the clockwise, one is the anti-clockwise. But here both are going to be anti-clockwise. And deflection in slope is 0, deflection 0 at the 3 location. That statement is also correct. But deflection 0 at the what now? 2 location and kinds of constant loads. In this case and in this case, deflection 0 only at the supports. But here deflection not only 0 at the supports, but is also 0 at the midspan. So I'm going to repeat this previous question now. Which of the following statement are correct when simply support beam subjected to concentrated moment at midspan? First statement is at the midspan, deflection is maximum, slope is 0. Most of students, they will select it now. Next, second statement, slope is maximum, deflection 0. Second statement is correct. Next, slope at the supports are equal and like in nature. Slope at the supports are equal and like in nature. Correct. B is correct, C is correct. And deflection is 0 at the 3 cross sections. That is also correct. Deflection is maximum at the and deflection is maximum between midspan and support. That is also correct. Deflection is maximum between support and midspan. That is also correct. Like this, so many 2 or 3 questions in the gate paper. That's given the span is given as a 2L is given. Should be careful. But all our equations are valid, span is L. When the span is given 2L, change it now. One question given, simply support beam subjected to point load at mid span. What is the maximum deflection? But span is given, 2L is given. Everybody is taken WLQ by 48 EI. But span is 2L. Mean what the answer now? WL cube, 2 to the power of L. 2 to the 2 cube means 8 will be there. So answer will be what now? WL cube by 6 EI you are going to get it. 48 EI the answer what when the span is L. But when the span is going to be 2L, equation is what? WL cube by 6 EI will be there. So should be careful now. Now for this case, what is the shape of the elastic curve? What is the shape of the elastic curve? A cantilever beam subjected to concentrated point load as well as concentrated moment. What is the shape of the elastic curve? These shapes are important in this chapter now. Already studied now. How many shapes are possible? Yesterday studied circular or parabola, straight line. Students are going to give randomly the answer. What you have studied in the conclusion page also I have given this tabular form I have given now. This tabular form I have given in the SFD BMD conclusions now. When EA is constant, EA is constant. When shear force bend 0, bend moment is 0. It is a straight line. When shear force 0, bend moment is constant, circular arc. When shear force non-zero, bend moment is varying, is a parabolic shape. When EA is constant, refer the table, summary table now. Shear force 0, yesterday I also discussed now, but I have not prepared the table, that is already there in the conclusions now. Shear force 0, bend moment is 0, R is the infinity, it is a straight line. When shear force 0, bend moment is a constant, it is a circular arc because R is constant. When shear force is non-zero, bend moment is what now? Varies, it is a parabola. So what is the shape of the curves here now? Most of the students, very few students are going to give the correct answer now. This will be straight line. So directly I am writing now. Check it now, all of you. You do it now. So this will be a circular arc. All the 3 shapes are possible here now. All the 3 shapes are possible. Here it will be a parabola. So the shape of the beam after bending between A and B, parabola, between B and C, circular arc, between C and D, straight line. How to decide it now? Any doubt? Draw the SFD and BMD. Here what a shear force and bend moment both are 0. Shear force 0, bend moment. Here what the shear force 0? Shear force 0 up to B. Here there is no constant point load. 0. Where the next constant point load? B. So D2B shear force 0. But D2C bendment is 0. But here bendment is there now. So D2C both shear force and bendment are 0. But C2B shear force 0, but bendment is a constant. And B2A shear force non-zero. Then bendment varies linearly. What the reaction now? Vertical reaction is W. Vertical reaction W. Moment reaction 0. WL, moment reaction is 0. So what the shape of the SFD? Here also bendment 0. Here also 0. Here what the bendment now? WL. Both are 0, straight line. 0 and constant, pure bending. Pure bending means circular arc. And constant varying is a simple bending. This is what now? AB is under simple bending. BC is under pure bending. But here both are 0. That's for the straight line, circular arc and parabola. Double integration method. So this one method we are going to study the three method: double integration, moment era method, and Castiglione theorem. Castiglione theorem is the simply extension of strain energy now. Double integration method. One by r equal to d square y by dx square. 1 by r equal to d square y by dx square. This is the actual equation. If you derive this now, how they got it now? They consider the elastic curve in the form of a parabola. Elastic curve in the form of a parabola. They got the relation between radius of curvature, slope and deflection. Y is the deflection, dy by dx a slope. So this is a relation. This is about a governing differential equation. Governing differential equation between the radius of curvature and the slope and deflection. R means radius of curvature of elastic curve. Y the deflection, and dy by dx is the slope. Slope is what? A tan theta equal to dy by dx. But generally we don't know the radius of curvature, we know the bendiment. What do you have studied now? M equal to, what do you have studied? The radius of curvature from bending equation. Radius of curvature equal to EI by M. So in place of this R, what should I substitute it now? Most of the question we know the bendiment. Radius of curvature is not known. R is equal to EI by M. Now if we can substitute it here now. In place of R, if I am going to substitute the EI by M, then what is this equation now? So most of the time you know the bendiment now. So this equation is used now. So if you know the bendiment, how to write down the bendiment equation is known. Already studied the last chapter now. So what the first step in this method now? Write down the bendiment equation, is substitute in this now. Then do the first time integration. First time integration will get the dy by dx. Slope you are going to get it. Second time integration. What the dy by dx integration? Y. Deflection. That's why this method is called the double integration method. So here to get the deflection you have to the two integration. First time integration of the equation you are going to get a slope, and second time integration you are going to get a deflection. So this method is what a simple, but number of steps are more. Is a simple method, but number of steps are more, just like a mathematics now. Governing differential equation. So while solving the problem, mostly you are using this equation. So what the first step this method now? Write down the bendiment equation that already have studied. Substitute this bendiment equation. Substitute the bendiment equation. Then integrate the equation. You are going to get a dy by dx. But when you are doing the integration, you are going to get a one constant C1. So to find out that C1, we need a boundary condition for slope. That is, we should know the where the slope is 0. We should know the where the slope is 0. Next time integration, we are going to get a deflection. We are going to get a one more constant C2. So here, if you want to get the slope, we should know the C1. To get a deflection, you should know the C2. C1 is determined by using the boundary condition of slope. C2 is determined by boundary condition of the deflection. So here what the requirement now? Students should know how to write down the bendiment equation. That already studied the last chapter now. Next, integrations are known. And what the other requirement? You should know the where the deflection is 0, where the slope is 0. So this method becomes simple If a student can identify, this method is valid when you know the location of zero slope and zero deflection. Zero slope and zero deflection. Always in cantilever beam, zero slope will be at the fixed end. Zero deflection also fixed end. So this method is more suitable for cantilever beams. But this method is suitable for simply support beam when symmetric loading. Symmetric loading. In case of symmetric loading where the slope is zero at the midspan. Default symmetric means you are taking about a constant loads only. So to find out the C1, I should know the where the slope is zero. Simply support beam where the slope is zero midspan in case of symmetric loading. So this method, but if a simply support beam unsymmetric loading, simply support beam unsymmetric loading, slope is zero between the point of application of load and midspan. So we don't know exact location of zero slope where this method is not suitable. That's why this method is modified by another scientist, what now? Macallis. That Macallis method is a modified double integration method. That method is compulsory for unsymmetric loading question. So this method should be used only when you know the location of zero slope. For every problem, do you know the location of zero deflection or zero slope? Every beam, we know the location of zero deflection. Every support deflection is zero. So always you know the boundary condition for deflection. But every support slope is not zero. Every support slope is not zero. Only fixed support slope is zero. Simple support slope is not zero now. So in every problem we know directly location of zero slope. That is, we know the boundary condition for the slope. So we know the boundary condition for deflection. We know that for every beam, we know the boundary condition for deflection. So we can find out the C2. For the C1 and C2 now constant. First time integration you are getting a slope. Then you are going to get a one constant C1. So want to find out the slope, we should know the C1. But if you want to know the C1, then you should know where the slope is zero. So all the beams where the slope is zero, now cantilever beam always slope is zero at the fixed support. But simply supported beam, you know the location of zero slope under symmetric loading. Simply support beam, you know the location of zero slope, symmetric loading. But when a unsymmetric loading, we don't know the location of zero slope. So for that question, this method is not valid now. Hence, this method is suitable when you know the location of zero slope. That is for all cantilever beam as well as simply supported beam symmetric loading. Simply support beam unsymmetric loading condition. Location of zero slope is unknown. Hence, this method is not valid. There, you have to go for a Macallis method now. Macallis method is modified this method only. Same equation, slightly rules are changed now. So Macallis method is a modified double integration method. That method is compulsory. That method is compulsory when the location of zero slope is unknown. That is simply support beam unsymmetric loading condition. That method is compulsory. What the first time integration of this equation now? What the first time integration now? Now this is what the slope. Slope is nothing but the tan theta. Tan theta. Tan theta equal to dy by dx. This is nothing but the slope. So to find out this slope, what is required? Now C1 is required. But to find out the C1, what is required? Now you should know the boundary condition for the slope is required. That is, you should know the location of zero slope. So in place of dy by dx, what you can also write down now? First time integration of this equation now. Generally EA is constant. EA is constant. Mostly beams are prismatic and same material. Flexural rigidity is constant. EA you are called the flexural rigidity. So what the first time integration now? dy by dx. But dy by dx equal tan theta. You have tried down the tan theta, but why you are writing theta? For smaller angle tan theta equal to theta. Actually you have tried down the tan theta, but for smaller angular deviation tan theta equal to theta. That's why you are writing the theta. Actually what the theta terminology? Angular deviation. But why you are calling the theta that slope now? Because for smaller angular deviation tan theta equal to theta. So here this is representing what a slope. So to determine the slope, what is required now? We should know the C1. So C1 is determined by boundary condition of slope. Boundary condition of slope. That is by using location of zero slope. Zero slope. That's why this method is suitable for all cantilever beam. All cantilever beam slope is zero at the fixed end. But this method is valid for simply support beam only under symmetric loading condition. Under unsymmetric loading, we don't know where the slope is zero. Next, for the first second term integration, C2. Now to find out the deflection, I should know the C2. So this C2 is determined by using boundary condition of slope. Here by using boundary condition of deflection. Boundary condition of deflection, that I am using the short form of BC. Boundary condition of deflection. That is by using location of zero deflection. Always we know deflection is where in the zero. Every support deflection is zero. Sometimes they are asking what now? What the governing differential equation in terms of shear force, slope and deflection? Is the governing differential equation in terms of radius of curvature, slope and deflection? Is the governing differential equation in terms of bending, slope and deflection? Now similarly, what is the governing differential equation in terms of shear force, slope and deflection? F equal to dm by dx. F equal to dm by dx means if we differentiate the equation, what you are getting now? F equal to dm by dx. If we differentiate, what you are getting now? F is equal to ei d cube y by dx cube. So what is the governing differential equation in terms of shear force, slope and deflection? Fxx equal to ei d cube y by dx cube. Means if I know the shear force, to get a deflection, how many integrations are required? 3 integrations are required. First time integration of shear force equation will get a bending. Second time integration will get a slope. Third time integration will get a deflection. Similarly, sometimes they are asking load intensity. Minus W equal to dF by dx. Minus W equal to dF by dx. Then what the equation now? Minus W xx equal to ei d to the power of 4 upon dx to the power of 4. Means when I know the load intensity, to get a deflection, 4 integrations are required now. But mostly we are using the equation. Always you know the bend moment directly now. And it will have the least integration. But if I know the shear force, 3 integrations are required. 3 constants you have to find out now. And if you go for the load intensity, 4 integrations are required. So here if I know the shear force, we know how to write down the shear force equation. We know how to write down the shear force equation. So if I know the shear force equation, first time integration will get a bending moment. Second time integration will get a slope. Third time integration will get a deflection. So to find out the deflection, 3 integrations are required now. Next. So if I know the load intensity, always in the question you know the load intensity. Whenever a UDL and UVL is there, no, load intensity is known. But what the drawback now? 4 time integrations are required. First time integration of the load intensity equation will get a shear force. Then you will get a C1. That C1 is going to be calculated by, C1 is determined by using the boundary condition of slope, sorry, shear force. And second time integration will get a bending moment. So to find out a bending moment, you should know the C2. Then third time integration, you are going to get the slope. Fourth time integration, you are going to get a deflection. So if you use this now, to get a deflection, 4 integrations are required. Means you have to find out the 4 constants are required now. That's why mostly this equation is used now. Always bending moment equation you can easily write down now. Bending moment equation easily can write down now. But this type of questions are generally for conventional. In the workbook there a question is given now. Load intensity equation is given. Find out the deflection. Load intensity equation is given. Find out the deflection. Means you have to do the 4 integration. First time integration shear force. Second time integration bending moment. Third time integration slope. And fourth time integration deflection. So first time integration you are going to get a shear force. We are going to get one constant C1. That C1 should be calculated by using the boundary condition of 0 shear force. That is, you should know where the shear force 0. And second integration will give the bending moment. So to find out the C2, you should know where the bending moment is 0. And third integration, you are going to get a C3. That C3 is going to be calculated by location of 0 slope. And fourth integration is going to get the deflection. To find out the deflection, you should know the where the deflection is going to be 0 now. So what the sign convention you are using here now? Default you are using this equation. What the sign convention? Already Bendment sign convention known. Now you need only slope and deflection sign convention. Bendment sign convention is sagging is positive, hogging is negative, already is known now. Sagging is positive, hogging is negative. Next, deflection. Deflection. Upward deflection is positive. Downward deflection negative. Means after twice integration I am getting a y is negative, means it is a downward. Next, slope. If theta is measured in anti-clockwise direction, is a positive. If theta is measured in clockwise direction, is a negative. Theta is measured in the clockwise direction, is going to be negative. So what the first step in, what the answer? Now write down the Bendment equation. Substitute in the governing differential equation. Next, first time integration. We are going to get one constant. That C1 is calculated by using the boundary condition of slope. That is, we should know the location of zero slope. Next, deflection, one more integration deflection. Then you are going to get a one more constant C2. So to find out the C2, you should know the where the deflection is zero. So what the drawback of this method now? This method is valid when you know the location of zero slope. This method is valid when you know the location of zero slope. Hence this method is valid for all cantilever problems. All cantilever problems, you know where the slope is zero at the fixed support. But this method is valid for simply support beam only under symmetric loading. Symmetric loading condition where the slope is zero mid span. So this method, double integration method, is valid when you know the location of zero slope. Location of zero slope. Hence this method is valid for all cantilever problems. All cantilever beams, any loading condition, because slope is zero at the fixed support. But this method is suitable for simply support beam under symmetric loading condition only. Only symmetric loading condition we know the location of zero slope, that is at the mid span. That is at the mid span. But unsymmetric loading, default unsymmetric means you are taking only constant loads only. TSL only you are taking now. Under unsymmetric loading, we don't know the location of zero slope. When the location of zero slope is unknown, this method is not valid. So to overcome this drawback only, another scientist, what the Michaelis, is modified this method. So what the other name for Michaelis method? A modified double integration method. Modified, slightly rules are, equation is same. M is equal to EI d square y by dx square. Equation is same, only the rules are changed right now. but that method is more suitable in conventional paper. But in objective examination, most of the questions are what now? 70% of the questions are cantilever beam, otherwise simply support beam symmetric loading condition. Few, only few, 2 or 3 times they have given an unsymmetric now. But I'm not discussing the mechanism now. Sir, then how to, so by chance I'm getting a question in the exam, unsymmetric loading. For that only we are going to discuss the Castigliano's theorem. Whenever you are getting a unsymmetric loading question of can simply supported beam, you can use the Castigliano's theorem. Castigliano's theorem is better than the Macaulay's method now. Macaulay's method bad, but conventional point of is better now. So in objective examination, getting the answer is not a criterion. Getting the correct answer within a less time. That's why I mentioned this method. Whatever I am giving the, you are only this chapter notes. This chapter notes is valid only for objective. But conventional, this chapter, whatever the notes you are getting, it is some more extra information required for conventional. Now we'll take a question on this now. One case I'm going to derive it now. This method is simple. What the drawback of this method is simple. Only what the requirement now. Write down the Bedimedi equation, substitute in the governing differential equation, do the integration, two integration, find out the C1 and C2. It's just like a mathematics. Just like mathematics integration now. But the requirements are students should write down the Bedimedi equation quickly and correctly. Next, you should know the boundary condition for slope and deflection. That is, you should identify where the slope and deflection are 0. Always cantilever beam both are 0 at the fixed support. Simply support beam symmetric loading, deflection are 0 at the supports. Deflections are always 0 at the supports. But slope is 0 at the midspan. Slope is 0 at the midspan. That's why I discuss all the starting 4 cases I discussed now. I will do one case for remaining all, you can do it on the same line now. Problem to problem only, Bedimedi equation will change now. For this case, for the tabular form third case, for the maximum slope and maximum deflection you have studied now. Maximum slope is WL square by 2 EI, slope deflection WLQ by 3 EI. Now that you are going to get it now. First draw the shape of the elastic curve. What the shape of the elastic curve? The Bedimedi is varying. Shear force constant, Bedimedi is varying. So it is a parabola. Is the elastic curve. YA will be Y max. Then how to get the slope? Now draw a tangent to the elastic curve. In which direction you have to measure now? You have to measure in such a direction that what now? Theta should be less than 90. In which direction is getting less than 90? Anti-clockwise direction. Anti-clockwise direction. And default you are assuming the EA is constant. What the first step now? Take a section, write down the Benjamin equation now. Then what the next step now? Write down the limits. What the limits now? 0 to L. So this is valid for entire beam AB. First step is to write down the Benjamin equation. Once you write down the Benjamin equation, this is simple now. Now can you give the boundary conditions here now? Boundary condition means you should know where the slope and deflections are 0 at the fixed support. At fixed support, both slope and deflection are 0. What is the meaning of this now? At x is equal to L, both are 0. X is equal to L, slope and deflection are 0. So you can find out C1 and C2 easily. And where they are maximum at x equal to 0. At x is equal to 0, both are maximum. At the free end is maximum. So what the next step now? This should be default EA is constant. I am taking the EA is outside now. Constant. What the MXX now? Now first time integration, default EA is a constant. All the equation whatever I have given in the tabular form, that's why I can check the title now. Constant EI. All that C1 and C2 are valid when EA is constant. So first time integration, EA is constant. What the integration of this now? dy by dx. This only you are calling a theta. Integrating this now. Integrating the equation to what the integration of this now? Minus wx square by 2 plus c1. Now to find out the slope, what is required now? C1 is required. This is the slope now. So we need the C1. Means how to find out the C1? You should know where the slope is 0. Where the slope is 0 at x is equal to L. At x is equal to L, that's the fixed end. Theta xx equal to theta b. 0. This is called the boundary condition. By substituting above boundary condition, BC means boundary condition. Already I used it now. BC means boundary condition. By substituting above boundary condition in equation 3. By substituting above boundary condition in equation 3. Then C1. Check it, WL square by 2. You'll get the C1. Now substitute the C1, then you are going to get a slope equation. By substituting value of C1 in equation 3. By substituting value of C1 equation 3. So if you can substitute, what you are getting now? So this is what now? Generalized equation for the slope. generalized equation for the slope. Mean with this one we can find generalized equation means we can calculate the slope at any cross section. What the limit for x now? 0 to L. So now we can substitute the any value of x between 0 and L. We can find out the slope now. But generally you are interested in maximum slope, where the slope is maximum at the free end. Then put the x is equal to 0. So this is called as what now? Generalized equation for slope. Generalized equation for slope. We want to get a maximum slope, substitute the x is equal to 0. If I put it x is equal to 0, this term is 0, then slope will be what now? WL square by 2a. That I will do it directly. I am going for the deflection. How to get a deflection? Integrate the equation now. Integrating equation 4. So integrating equation 4. What the integration of this now? Y x cube by 6 and WL square by 2 into x plus C2. Plus C2. Now to get a deflection, what is required now? C2. C2 the boundary condition for, so C2 is determined by using the boundary condition of deflection. So where the deflection 0 once again at the fixed end, that is at x is equal to L. Yxx equal to yb is 0. Now by substituting above boundary condition in equation 5. Check it, you are going to get the C2 minus WL cube by 3 minus WL cube by 3. Now by substituting the C2 value, value of C2 in equation 5. So now this is a generalized equation for deflection. Generalized equation for deflection. Now with this one we can find out the deflection at any cross section, but default you are interested in maximum deflection. Both slope and deflection are maximum at the free end. So 2 at x is equal to 0, theta xx equal to theta max, and y xx equal to y max. Now substitute these two in equation 4 and 5. It is the 6. By substituting above in equation by substituting these two in equation 4 and 6. If I put it 0, so what the maximum slope? Now WL square by 2a. And if I put the x is equal to 0, this is 0, this is 0. So deflection is WL cube by 3ei. From equation 4. So this only you are calling as a C1. I am getting a positive. What is the meaning of positive? Anti-clockwise rotation. So by chance you are getting a negative means clockwise. Similarly from equation 5. So equation 6. I am getting a negative. Negative means the downward. So this you are calling as a C2. C2. This is only given in the tabular form 3 now. Tabular form third case. Negative means downward deflection. We have taken a positive deflection is what? Upward. So now beam to beam, which condition will change now? Beam to beam, problem to problem, bendment equation will change. Then boundary condition will change. Boundary condition for slope and deflection will change now. So remaining is simple. So once a student is thorough with bendment equation that already I studied the last chapter, now only should identify where the slope and deflection 0. Once you know where the slope and deflection 0, you can find out the C1 and C2. Now we can make some important conclusions here now. So like this, what the remaining all the case in the tabular form UDL and UVL, you can try it now. If you go for a UDL, cantilever beam UDL, what the bendment equation? When a UDL is there, what the bendment equation now? Minus WX square by 2. Minus WX square by 2. So already I studied all this thing now. So those who want to get that equations, whatever I given in the tabular form, so you can do it like this now. Only change the bendment equation now. So for this case, we'll make some conclusions here now, so that you can easily remember that all the formulas now. I'm getting a positive means anti-clockwise. So Suppose if I am getting a positive means upward, I am getting a negative means downward. Next, if you want to get the stiffness, starting you have studied now, axial stiffness, torsional stiffness and flexural stiffness. What the stiffness of the beam now? Flexural stiffness, W by Y max. These definitions are discussed now. When you have studied the deflection stiffness, you have studied is the flexural stiffness of the beam under constant point load, W by Y max, 3 EI by L cube. Now from this three equation, what the conclusion now? Slope and deflection are inversely proportional to EI. Change in length is inversely proportional to axial rigidity. Angle of twist inversely proportional to torsional rigidity. But slope and deflections are inversely proportional to flexural rigidity. And flexural stiffness proportional to EI. Axial stiffness proportional to AE. Torsional stiffness proportional to GJ. Similarly, flexural stiffness proportional to EI. So what the meaning of this now? Higher the flexural stiffness, flexural rigidity. EI is called the flexural rigidity. Higher the flexural rigidity. What happens now? Slope and deflection both are going to be less, but stiffness increase. There is a question in the fourth question in the workbook now. Higher flexural rigidity is a indicative of higher flexural rigidity means slope is stiffness is more, and slope and deflection are less. More EI means more stiffness. More stiffness means less deflection. Less deflection means less slope will be there now. Now, Y max and theta max. Inversely proportional to EI. So always in the denominator, what should I take in EI? For all the problem in denominator EI. Next, stiffness is proportional to EI. EI is called the flexural stiffness. Sorry, flexural rigidity. EI is about a flexural rigidity. Kf is the flexural stiffness. Higher the flexural rigidity, higher stiffness, then lower slope and lower deflection. So always we need a beam with a higher flexural rigidity is required. Higher flexural rigidity. Now, how to remember this equation? You can check it now. But the one more conclusion now. Slope is proportional to Lz. Always in the denominator, what should I write? EI. And numerator, what should I write? A corresponding load. But the corresponding load here, a constant point load means W. If a constant moment means M. If a UDL and UVL means small w. So numerator I have to take the corresponding load. When a constant point load means W, concentrated moment means M, and UDL and UVL means small w. Denominator, what should I take it now? EI. EI. Then next, deflection is one order higher than slope, because we are getting deflection by integrating the slope equation. So deflection is always one order higher than slope. Here the L square, L cube. So in case of concentrated point loads, slope is proportional to L square. Deflection is proportional to L cube. But if you go for a concentrated moment, that is a bending couple, slope is proportional to L. Deflection is going to be L square. Under concentrated moment, slope is proportional to L. Deflection is proportional to L square. Under concentrated point load, L square and L cube. Concentrated moments, L and L square. And UDL and UVL, L cube and L to the power of 4. UVL and UDL, L cube and L to the power of 4. So only the students should remember this C1 and C2. You are called as about now. So finally the students should remember the C1 and C2. So we remember the C1 and C2 now. all the equation you can directly can write down. How to remember it now? When a constant moment, first what used to be there now? Numerator corresponding load. Constant moment means M. Constant point load means W. UDL and UVL means small w. Denominator EI. Then how to decide L, L square, L cube now? Concentrated moments. Slope is proportional to L. Slope is proportional to L. Deflection is going to be L square. And constant point load. Slope is proportional to L square. Deflection is L cube. Constant distributed load. L cube and L to the power of 4 will be there now. But what the assumptions you have made now? What the assumptions you have made it here now? When the equation is valid, first you assume the EA is constant, that EA you have taken outside the integration. So all the equations are valid what now? When EA is constant. Suppose a tapered cantilever beam is given now, same load. But if a tapered cantilever beam is given, the equation not valid now. So all the equation, whatever I given in the tabular form, valid when flexural rigidity is constant. That is same material, same cross section. Flexural rigidity is constant. Next, which one is neglected now? Shear force affected here. Shear force also going to be there now. So these are all slope and deflection due to bendment. Slope and deflection due to shear force is neglected. So these equations are going to give the maximum slope and maximum deflection for a cantilever beam subjected to point load when EA is constant and neglecting the shear force effect now. Neglecting the shear force effect. Now I'm writing the generalized equations now. Now whatever I'm writing, if you have prepared the table, I have uploaded the table now. So back side of that page you can write down this now, so that all are going to be sufficient at a place will be there now. In the tabular form I have given both a C1 and C2 now. So just now whatever I'm writing, this you also write down at the back side of the tabular form under concentrated moments, or what is the name now? Bending couples. Bending couples. Some students are going for the boundary condition. Sorry, you use the boundary condition. Bending couples. When flexural rigidity is constant, flexural rigidity is constant, theta max, what should take the numerator? M. Denominator numerator corresponding load, denominator EI, and it should be L, ML by EI. Then constant will be there. That constant you are calling as C1. Then when you are going for slope, what change you have to make it now? For slope, what I have to do it now? One order higher. So it should be ML square by C2EI, one order higher. ML square upon C2 into EI. Default is what now? About neutral axis. So only what change now? One order higher, and C1 should be replaced by C2. C1 should be replaced by C2. Then what is the stiffness now? Stiffness is what now? Just like what now? torsion, what the torsional stiffness T by theta. Here also what the stiffness now M by theta. This is already explained now. Bending required for a unit slope of 1 radian. So this will be when you go for a concentrated point load. Constant point load, what change you have to make it now? In place of MW. Now there is the L square and the L cube. C1 and C2 are changes. And when you are going for a UDL and UVL, in place of M, small w. L cube and L to the power of 4. Like that you can easily remember it now. Otherwise if you want to by-heart the total equation difficult now. Only you have to remember the constants only. Under concentrated point loads. Under concentrated point loads. Numerator corresponding load. W. Now previous L means one order here L square. C1 EI. And what about the deflection? What change you have to make it? Now one order higher. Always slope is one order higher. Deflection is one order higher than the slope. If the L square means this should be L cube. And your stiffness is here only most of students are going to write down EI by L. It is the EI by L cube. EI by L is valid under concentrated moments, but here the L cube will be there. Next, under distributed loads. That is UDL and UVL. Distributed loads. Theta max. What the numerator? Now small w. Is the L, L square and L cube should be there now. C1 EI. And what the Y max? One order higher. Previously L cube means L to the power of 4. And C2. But what the small w in case of UDL? Sometimes they are going to give the total load is given. Sometimes total load is given in the question. What the small w in case of UDL, if total load is given now, W by L, capital W is about a total load. So should be careful. In the question they are giving the intensity or total load. 2 or 3 questions in the gate paper they are given a total load is given. Total load means become as a constant point load. And what the small w here now? Whenever a UDL and UVL is given, you should be careful. If a constant total load is given, then this will become as L square and L cube. So capital W is the total load. So if it is given, total load is given, small w should be replaced by capital W by L. In case of UVL case, what the total load? WL by 2. So if the total load is given, what the small w? No, 2W by L. If the total load is given, once again total load become as a constant load, then this will become as L square and L cube. So you should be careful whether they are giving the total load or load intensity. Finally, what the Y max by theta max? Do I need the Y max equation or theta max, or both are required, or one is sufficient? Do I need the Y max or theta max, or both are one is sufficient? One is sufficient. Y max by theta max is equal to y max by theta max equal to C1 by C2 into L. Some question directly they are giving the theta max. Find out the y max. Then if you know C1 and C2 directly can calculate it now. So based upon this also some questions are there in the workbook as well as especially engineering service, and one of the gate paper also the question is there now. Only 1 minute. Only one question I am going to take it. Kf is not defined there now. Under and not written the Kf. Kf is about the flexural stiffness. Here we cannot define it now. Kf cannot be defined in case of distributed load. So now one question is given like this. Determine maximum slope when a simply supported beam is subjected to concentrated point load at midspan. Concentrated point load at midspan. Midspan. If maximum deflection is 5 mm, span is 5 meters. That's all. This question is given now. Most of students they left it now. Sir, insufficient data, sir. W value is not given, E is not given, I is not given. What is given now? Determine the maximum slope when a simply SSB means simply support beam subjected to constant point load at midspan. Y max is 5 mm. Slope is what? A span is 5 meters. Now you have to find out directly what you have to do it now. Y max by theta max. Now you can substitute it now. Theta max you have to calculate now. What the Y max is given now? 5 mm. But the C1 and C2, see the tabular form. By this time, some students you might have by-hearted that C1 and C2 now. But the C1 and C2, see the tabular form. All of you keep that tomorrow. Either you by-heart that C1, C2 values, otherwise keep the tabular form in front of you. Make a copy on your own now. Otherwise, you cannot do this question now. Without knowing the C1 and C2, this question cannot be completed. So for simply support beam, probably see the fifth, 1, 2, fourth case. See the fourth case mostly now. In that I'm not remember the exact sequence, maybe fourth case now. C1 is what? A 16. C2 is 48. Length is how much is given? A span is given 5 meters. So what the theta max now? Theta max is what now? So I made a small mistake. So it should be Y max by theta max. Sorry. That's why you are getting in different now. Y max by theta max. Y max is 5. So theta max is that is radians. Check it is okay, 0.003 will be there. Point 0.003 radians, 0.003 radians. Sometimes they may give it the units are radians. You have to convert. If you ask degrees, you can, but mostly they will ask the radians. Without knowing the C1 and C2, you cannot complete this question now. Like this, so many questions are going to be there now. I rectified my mistake. I have wrote now. Initially, I written theta max by y max. So today's lecture, I'm going to close it. But even though I'm taking 1 hour more than the allotted 1.5 hour more, but still, I thought that by today this chapter should have completed. Then I expected by tomorrow and will complete it. But still, I'm lagging by 4 hours. I don't know how to complete it now. By day after tomorrow now. So till this chapter will take the 6 hours of time. So tomorrow we'll try to complete the year. Maybe 3-4 hours still maybe lagging. We'll see it. We'll try to do it now. So tomorrow, before coming to the class, now you can complete all the questions of SFD BMD. SFD BMD. Next, based upon this deflection of the beam class, you can complete these questions now. I'm suggesting once again what now? You by heart that C1 and C2 formulas now. By heart the C1 and C2. Otherwise total formulas. Remembered. There are 10 or 11 cases are there that you have to compulsory should be remembered it now. Now complete the total SFD BMD, and from the deflection of the beam chapter you can complete these questions now. Chapter number 4. Based upon whatever I discussed, it can complete question number 4. Not 4, sir, 5. Question number 5. Question number 23 and 32. Question number 39, what is given? A load intensity is given. Load intensity is given. A simply subbed beam load intensity is given. Asked to find out the deflection. When a load intensity is given to get a deflection, how many integration of 4? First time integration that I am not doing. Generally these questions are question number 39. Generally not possible for objective. Mostly conventional is going to be there. But some of the test series paper they are giving. So some of the students are asking, sir, this type of questions here not. That's why I framed a question now. So load intensity is given. First time integration you will get a shear force. Then second time integration you are going to get a bending. Third time integration you are going to get a slope, fourth term integration, deflection. Then you have to the four constants C1, C2, C3, C4. C1 is calculated by location of 0 shear force. C2 is calculated by location of 0 bendment. Always simply support beam where the bendment is 0, at the ends bendment is 0. We don't know where the shear force 0. But always bendment is 0 at the simply supported end. Means at x equal to 0, bendment is 0, x equal to L, bendment is 0. Always simply support beam, we don't know where the shear force 0. But always you know the what now? At the supports bendment is 0. As x is equal to 0, bendment is 0, x is equal to L, bendment is 0. So with that one we can find out the C1 and C2. Next, and where the, once again we cannot find out the where the slope is 0, but we know where the deflection is 0. Deflection is 0 where now? At the support, at both the support deflection is 0. So by using these conditions you have to find out the C1, C2, C3, C4 now. Then we can get the maximum deflection equation now. So this question you can complete it now. So these questions you complete it. These are the homework only. This you can complete based upon the today's class now. Based upon today's class, as well as chapter number 5. Now you got the maximum chapter number 5. Some questions are pending based upon this chapter. SFD BMD 13, 19, 21. So these questions, these are what based upon the SFD BMD. These questions were pending because by that time you are not complete the SFD BMD. Next, 25. 25 is important now. 26, 27. Next, similarly, chapter number 6. Already I have done this question in the class now. Question number 12 and question number 29. So with this one, chapter number total 6 is completed. And chapter number 3, SFD BMD can complete it now. These questions you can complete it now. So today's lecture is completed. So we'll continue tomorrow once again at the same timing, 8 o'clock. Once again, before tomorrow, otherwise if you are not remembered that C1 and C2 now, try to by heart that C1 and C2, but if you are unable to by heart it, keep the tabular form in front of you. Prepare the tabular form in front of you. Otherwise tomorrow's lecture is going to be very difficult to follow because all the questions are going to be 80% of the questions are based upon C1 and C2 only. That constants. So that should be compulsory. So tomorrow we are going to complete the deflection of the beam. Then you are going to take one more thermal stress or the shear stress in the beam topic you are going to discuss tomorrow now. And last 3 chapters will take the 6 to 7 hours only. Theories of failure, all the basics are completed. Theories of failure, columns as well as pressure vessels, thin pressure vessels. These 3 topics will take maximum 6 to 7 hours only. So don't bother, we'll try to complete it. If any portion is there, we'll try to find out. But I'm not going to cut down. Everything is going to be discussed systematically. All the batches, how I am able to do it. Here also I'm good. But still I'm giving the more information only. So thank you one and all. We'll meet tomorrow. Today's lecture is completed. So many questions to be completed. If any queries,